Hello, everybody. In this video, we will train a neural network that will predict the binding affinity from a protein-ligand crystal structures. So this tutorial I'm basing on from the book called Deep Learning for the Life Sciences. I would highly recommend for you to visit this book if you're trying to apply machine learning to some biological problems. This is a great book. And for this particular tutorial, I'm using pdbbind datasets. We will be importing this datasets and we'll be creating model using our Deepchem package. Now, if you haven't visited Deepchem package, you should. This has a lot of things that you can apply. So my favorite part is the MolNet datasets. So you can see here, this has a lot of datasets that you can directly import using the Deepchem codes. So I have made a video on TOX21 datasets. You should check it out. And also I have made a video on the Delaney datasets where we predict solubilities. And then I have also, so in this video, I'm making our pdbbind datasets. Now this pdbbind datasets has 3 sets of data. So if you notice here, it has core set, which has only 193 complex. This is very curated. So this is what we will be doing. So this core set will not give us good data, of course, but this tutorial is for only informations, not to get a good data. It just make sure that things are working. I would recommend you should try with this 4,852 protein-ligand complexes, which is called as refined set. Like it will take about 2 to 3 hours to featurize the molecule, depending upon your PC, maybe longer than that. And then I'll not touch this 12,800 complex, which is our general set. Now this has going to have a lot of incomplete data. It probably will not be worth the time, but it's there if you want to do it. Okay. So let's go back. So here I'll be using Deepchem. So in my next video, I will create a tutorial how to install and Deepchem package. So for this particular tutorial, you definitely need this PDB fixer. So you need to install this before you can do this. And you want to make sure you have PyTorch installed as well. So PDB fixer is going to fix the some of the problems with PDB. If you don't, you're going to have a bunch of empty arrays will be attached to your data, and that's the problem a lot of people were having, the empty array problem. And you want to make sure your NumPy is below 1.25, minus 1.24. Okay, so let's begin. Let's import our Deepchem. So Deepchem, once it's imported, so first thing we're going to be doing is featurizing our molecule. So let's create a featurizer. So Deepchem has a lot of featurizers built into it. So in this case, we're going to be using our RDKit featurizers. Now, what this does is it takes the crystal structures, which is in this case the PDB file, and it's going to convert into some sort of numbers based on physical and chemical properties of that enzyme ligand complex, right? So in this case, we need to assign a few parameters. So first thing that we're going to be doing is voxel width. It's going to be 2.0 angstrom. Now, what is a voxel? So voxel is a 3-dimensional counterpart of pixel. We all know what a pixel is. Pixel is a square in our 2-dimensional pictures, right? Voxel, on the other hand, is a cube in a 3-dimensional space. So we want a cube of 2 angstroms. So angstrom is 10 to the power negative 10 meters, in case you have forgotten. So voxel width is 2.0. The next thing is feature type. So what are the features we're going to be applying to our molecules? So we'll be applying voxel features right here. So these are list of voxel feature you can call. So I'm just going to copy paste this, and I'm going to remove few of these. So I want to keep it a little bit simple for this tutorial. You can mess around with it. What features do you think important? For example, pi stack is important when there is hydrophobic interactions, or especially with the DNA RNA complexes where protein is interacting with DNA RNAs. I'm going to removing cation pi as well, where the pi bonds interacting with A cations. And I'm going to keep it simple. So this will not cause too many problems. Okay. And then next thing is flatten equals to true. So which means basically we are featurizing our molecules with all these, and then we are just converting into a one-dimensional arrays. It's just one straight numbers. And the last thing we're going to be doing is sanitize equals to true as well. So it will clean up our data if there is anything. Sometimes in the crystal structures, the PDB files are extremely messy. It's sometimes it will say, oh, it has 5 bonds in a carbon atom. And if you remember, carbon can have only 4 bonds. So it will featurize. So we have defined our featurizers. So you can look at other featurizers as well. There are a cheat sheet that you can explore on their website, which featurizers works for which type of model. Like you cannot mix and match, but you want to make sure your featurizers matches with the model that you will be using. So we will be using today a multitask regressor model. So this matches with our grid featurizers. Okay, so let's begin. First thing we're going to do is load our data sets, task, datasets, and transformers is going to be deepchem.molnet. So this is the code that you can use to load any data. So you can see all this we can be using. So in this case, today we are using pdbbind. Now it needs few parameters. Obviously, the first one is featurizers. It's going to be the featurizer we just created. So this is the featurizers we can apply. Let's look at what else. Transformers, it's applying a normalization transformers. Splitter is applying a random splitter. Reload equals to true or false. So again, this is something you wanna check which works for you. So if you put reload equals to true, it will first check if your temp folder has this file already somewhere in theirs, right? So this data sets. So if you have previously used this, previously tried this tutorial on your computer and it didn't work, maybe you want to put that into false. Then it will fresh download. Okay, I always put that as false. And then let's look at what else do we need. Set name. So we are doing today core. You can work with refined, but just make sure it's going to take some time. So set name equals to core. I think that's all we need to do. So this will take about 2 to 3 minutes, depending upon your PC. It may take 10 minutes if you have a slow computer. So I will fast forward to this once this is done. Okay, we are back. So it took about 3 minutes on my computer. So let's begin. So you can see here, so we have loaded our data sets. So you can check the task. So the task is our binding affinity, which is negative log of KD divided by KE. So it has only one task, and that's important. You can you can have multiple tasks sometimes. Let's look at our transformers. Just like we said, the transformer should be normalizations transformer. So you can see it has a normalization transformer attached to it. And let's say, let's split our data sets into train, valid, and test. So train, valid, and test equals, so this has already splitted, but we're just loading it now, data sets. So in Deepchem, you can access the data sets by calling it out train.x. So now you can see it has train, it has all those data sets. But here's the catch. So look at the data type here. It's int 8. So you can find the data type as here print data type. Now this is going to cause a big problem in a second, and you need to take care of this before you build your model. So I'm going to look at train.y, train.w. W is the weights that's attached to it. Okay, so you can see x is int 8, y is float 64, and w is float 32. So you need to make sure all of the data types are same before you can do math with it. So when you're building a model, you have to do a lot of matrix multiplications, and you want to make sure all of you are in the same type of data, like int and float. They are not compatible with each other. So these are basically NumPy arrays, right? So we can easily convert them into one type of data and repackage them just like Deepchem wanted it. So let's do this. So this is the first thing we have to do. So let's create xtrain equals to train.x.astype. So we are changing this to, I'm just putting everything into float 32. You can pick whatever you want. Let's do this for everybody. Control V, Control V. So what I am doing here is, so let me explain. Let's change this to W. Okay, so I'm creating 3 new NumPy arrays, xtrain, ytrain, wtrain with float 32. And I'm gonna do this for same as well. If you notice, the W is already 32, just doing it to make it look cleaner. And we wanna make sure every time we do this is correct. So test, 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 and test. Okay, so everybody is float 32 now, and we can make sure it's xtrain.dtype is float 32. And you want to make sure the train.x here, the one that we had before, like train.x.shape is, oh, not s, sorry. Train.x.shape is 154 and 18,432. Okay, now we got 154 molecules in there, and we have 18,432 features in there. So that was straight out of here when we load. And we want to make sure that we still have the same data, right? So our data is shape, xtrain.shape, and it's the same thing, right? Okay, so now we need to repackage this xtrain, ytrain, wtrain into a datasets type object that's gonna be read by our Deepchem. So you can very easily do this. Let's create something train datasets, and you can do this by calling data module. And because these are NumPy arrays, so let's bring in, so we're gonna load NumPy datasets into this, and it needs x, y, and w. So our x is xtrain, ytrain, and wtrains. All right. So let's do this for our test datasets. I'm ignoring the valid portions. That's not relevant. That's not going to be relevant for this tutorial. You can add those valid to, you should add those valid to your train datasets if you don't want to do it. Okay, so x test, y test, and w test. There we go. Okay, so we have our train datasets, and you can see I could call train dataset.x.shape to see that it's the same number, 154 molecules, 18,432 features. And I can see my task, 154 tasks I have, right? So, yep, so we have formatted our data types. So we are good to go to build our model. Okay, so let's build our model. So Deepchem has a lot of models, and you want to make sure in your Conda environment, which I'm using right now, you want to make sure you have PyTorch installed. If you don't have PyTorch, then you're not going to get access to this model, because this model is a multitask regressors model, and it uses PyTorch in its backend. So if you don't have PyTorch, this model will not show up. Okay, so you want to make sure you have multitask regressors, sorry, PyTorch installed in it. So let's see, what are the parameters we need? So first things we need is end task. So how many tasks we have? So if you remember, we have only one task. Because this is a multi-class, you can add more classes. You want to predict a bunch of different things if you want to. But this is one task, simples. So how many features we have? So you can see here our data sets has 18,432 features, 18,432. You don't have to put 18,432. You could just call it xtrain dot, sorry, not xtrain, train datasets dot x dot shape index number 1. So that's basically we are adding this, and first index is 18,432. This is 154 is 0th index, and this is going to be our first index. Okay, so that's good. Let's see what else we can add. We can add dropouts, or let's add the layers. How many layers we want? So we want, so that these are dense layers, so you can provide a list here, list of numbers. So on my first layer, we're gonna have 2000s. Let's make it 5000s. Then next, I'm gonna add 2000. You can test which works best for you. I know this probably gave me the best so far, 5,000, 2,000, 1,000. And let's add dropouts, 0.5. So we got 3 hidden layers, and our dropouts, we are randomly dropping 50% of our data sets, right? So that would kind of make our model better by preventing overfitting. Okay, so our model looks good. So all we have to do now is call the fit functions, model.fit, and all we have to do is train data sets. Let's call our train data sets. Remember the Deepchem data has packaged our train data sets, which has everything, xtrain, ytrain, and wtrain, the weights. So it's good to go. We don't need to assign xtrain, ytrains. And last thing we want to make sure is number of epochs. So how many epochs you want in your model? I'm just going to say 200, maybe more than enough. What's an epoch? So epoch is our model will pass this all of the 154 molecules through it. So that's one epoch. And we are doing this 200 times. So you're passing one after another 200 times, the entire batch. Okay, and let's do it. It's gonna take about a minute, and I will fast forward. All right, we are back. It didn't take about a minute, it took 30 seconds to train this model. So our model is trained. So let's see. So this gives us the return was loss function. So you can see it will return average loss over the most recent checkpoint. So this looks pretty good, 0.06. So let's evaluate our model. So we're going to evaluate our model. So to evaluate model, we need to define a matrix. So a metric. So how are we going to evaluate? So let's create a metric. And Deepchem has a lot of wrapper class, dc.metrics. So this is the metric class that would serve as a wrapper class. And we're going to be doing the Pearson's R2 score. Okay, dc.metrics Pearson R2 score. So we'll be using this to evaluate our model. So let's define our train score is going to be model.evaluate. And to evaluate, we're going to be using our train data sets, and the metric we will be using is the one that we just defined. And we want to make sure, we want to tell our model that we are using our transformers equals to transformers. So that's the transformers. We want to make sure it's there. So let's print our train score. So you can see we got 99.99. Obviously 1 is the best. So here, obviously it's overfitting, right? So let's try on our test data. Let's evaluate our test data, model.evaluate, and test data sets. And we'll be using metric, the same thing. We'll be using transformers as well. And let's print our test score. And let's see. Okay, 0.229. Okay, this is not bad. Again, these numbers, sometimes you get lucky, sometimes you don't, because this is a extremely small data sets, right? 154. If you notice our test data sets, if you want to look at the X test, so train data sets dot y dot shape, this has only, not y, X. And now if you look at our test data sets, it has only 20 molecules, right? So 20 molecules in this, and we are splitting randomly. Sometimes you might get a couple of bad molecules, and that 1 or 2 bad molecules will change your R2 score by a huge margin. I have got sometimes 30, sometimes 33, 37. So one solution would be, when you split, you want to make sure you are splitting the exact same way so that you can build, or you could just use the bigger batch. Instead of core set with only 200 molecules, you can use the bigger batch, 4,000 molecule, and that's going to split differently. And you're going to have, when you have a large number of molecules, that would definitely give you a better Pearson R2 score. You want to be as close to as possible to 1. Okay, like this one. So 0.22 out of the box is not bad at all. So let's build something. Let's look at our data. So let's predict. So let's create something called predictions, and we can do this model.predict on batch. So our batch is xtest. Our batch is test datasets dot y. Okay, so our batch is predictions model dot test datasets dot y. Oh wait, not y. Test datasets dot x. So we are predicting on this batch, right? So let's see. Let's print our predictions. It's gonna be. Let's look at the first 5 predictions, and we got our first 5 predictions right here. Let's compare that with our y test. Test datasets dot y, and you can see this is an array, so these are the same number. So looking okay, I would say. Well, our R2 score was not great to begin with, but this is reasonable considering the smaller number of data sets we have. Okay, so let's maybe we should do is let's plot these, right? So let's plot this. Let's plot them in a graph, see how it looks like. So let's import matplotlib dot pyplot as plt. I like to Seaborn as SNS. I like Seaborn a lot. So figure axis equals to plt.subplots, and we want fixed size to be 5 out of 5. Okay, and let's define x. Let's create a regression plot. Rig plot, or you can do scatter plot. Well, why not scatter plot? Okay, scatter plot. And here our x is AX is going to be train data sets. X axis is going to be the true value, which is test data sets dot y, and our y would be predictions. And let's define AX equals to SNS, set title. We're gonna be set title, so let's call it pdbbind dataset, and set label, set x label, ex dot set x label. So x label is true. Ax dot set y label is going to be our predictions. Okay, so there was some, pre-columnar must be 1 damage. Now I see. So you notice here our predictions has, it's putting 3 brackets, so it's a kind of 3-dimensional array, so this didn't like it. So we can just reshape it, predictions, and might try it. I think I remember the regression plot had okay, so that's kind of the similar things, but it just added a line to show how well they're fitting. So you can hear this number here, it's predicting to be the true value is about 0.5, 5.6, but this is predicting to be around 0.5. So this is the regressions lines around here. Or we could try converting this, reshaping. So let's reshape. So predictions equals to prediction dot reshape. So you can see here print predictions dot shape. Okay, prediction dot shape. So it's 21 ones. It's a 3-dimensional matrix. We just gonna reshape it to 20. And we can print it out. Okay, so now it's 20. So if we do a scatter plot, x test, there we go. So we have a scatter plot right there. So it's not good. So you want them to fall as close to the linear, like in the diagonal. Obviously, we have to change the axis to match perfectly, but it's not bad out of the box. All right, so I will post this code in my GitHub page. And again, big shout out for Deep Learning for the Life Sciences, the book, and the creator of pdbbind datasets. And I will provide a link to install PDB fixers. And in my next video, I will create a tutorial how to install some of the basic packages that is required for this tutorial and in Deepchem in general by using condas, mini condas. All right, so that's all I have for this video. Thank you.